Lunch. Sometimes I am here in this place to act as a writer, and therefore I would like to say something about this institution. Also because this year we celebrated the 40th birthday of this institution, the 40th anniversary. And this non-profit institution was founded in 1970, but the idea of creating or generating a place with the present mission came in a meeting in Poland. So how many attendees from Poland? Could you? From Poland? Who is from Poland? Nobody? That's interesting, because in Poland the origin, but also was rather they played an important role in the foundation of CISM. And so in persons, I would like mechanicians, Professor Mechanics, I would like to mention, reminder to you, you heard probably, was Professor Olszak from the Polish Academy of Science. Ciao! Ciao. Sorry for the interruption. This is Professor Pierre, yes, who is a member of the Scientific Council of the system. So I was telling you something about the origin and primarily Polish scientists, particularly Professor Olszak at that time, but also now well known in solid mechanics. We're interacting with two Italian professors. One was in Pietro Brescia, so-called time pressure, and the other well known as a leader of the astronautical engineering in this country, Italy. Incidentally, I have my student who was in Rome, so I remember them. They interacted with colleagues from other countries, and at that time, particularly the Polish Academy of Sciences. And they succeeded in getting the approval of the administrative and political authorities in this country, particularly in this region. And so they started CISM. It's a mission which was and is still the transfer through courses like this one. Recently achieved research results from, well, not necessarily all people, but anyway, international acknowledged research leaders, like lecturers in this course, to young people, so postdocs, etc. So this, in this sense, as far as I know, this institution is rather unique in the community, international community of, let's say, theoretical and applied mechanics. Yes. Then I would like to remind you, because of that, there was in 1976 a terrible earthquake in this region with 700 people killed, not in this town, but around. And of course, for reconstruction, a special effort was needed from the engineering community, particularly in this area. And CISM started that time, and now continuously, to organize also so-called advanced professional training for engineers, most in Italian, not in English. And after the earthquake, this contributed to the reconstruction. So there are these two streams of activities. One, the advanced courses, like this one, of course, And there are other courses for practicing engineers, still now, particularly in winter. And also participation in research, but by the staff of the university, etc., started in recent years in research project, particularly European research project, with the participation of CISM as a place where to meet, etc. Stuff here, here, or here, okay, in the future probably. Well, another aspect, you can pick up also the booklet which was updated this year because of this 40th anniversary, yes. Another, yes, information that I believe it is not trivial to provide you is about this building and the event which made this building in older times rather well known in this area. Why? Because in 1606, so the local in the region, this town, the local scholars, let us say, founded an academy. This occurred 3 years after the foundation in Rome by the pupils of Galileo Galilei, our present National Academy of the Lincei, yes, at that time. Then the Latin did not write so much, but anyway, after the death of Galileo Galilei, but anyway, the Academy of Lincei was one of the first official academies and then Royal Society later in London. But 3 years after this event by a young man, Chesi, pupil of Galileo Galilei in Rome, and here. However, and in this building, the members of the academy used to come here and to discuss not variation methods, rather poems, philosophy, literature, etc. Yes, variation method came later as a subject in this book. However, the paintings that you see around were produced about more than 1 century later. This building was restored, and the academy in 18th century started to meet here for reasons that so it was a little in a sense restored. However, it was refounded, and now there is a local academy which meets here sometimes for, yes, but not as celebrated in the history of like when it was founded in the 17th century. So if you have a look around, you can see this painting which were produced primarily in 18th century and later video from this one. Okay, now I stop how to say using your time, which can be used for important tasks. And of course I wish you the success of this course, which is of course is focusing rather timely and important subjects in mechanics, ratio mechanics, with 4 hours in relationship. Let's hope ratio engineering mechanics have a pleasant stay this week. Then we'll be brief at midday in order to give to attendees and actual opportunities to interact. So here, somewhere here. So good. So have great fun in this course. Good. Thank you, Francisco.
before I thank Professor Meyer for having organized as a rector this school of CISM and the scientific committee and everybody who worked for this. I should start maybe immediately with talking about the subject. I decided to start with 45 minutes of introduction about the topics and the problems and the philosophy which is gathering all the lecturers here. Of course, I had no time, or maybe we decided it was not so important, to discuss these points with Professor Berdichevsky or with Professor Frankfurt. I'm rather sure that they agree with the majority of the statement, but in any case, discussion is open and it is important also discussing. You never need to be in agreement, especially in science, a priori. I needed to choose what to say at the beginning. Two possibilities are usually available. Either you start with very complicated stuff so that you are considered very serious. Maybe not everybody will understand all details, or if you are good enough, nobody will understand anything. And this will make you in the situation of the Maya priest who is not understood by anybody and therefore is powerful. The other risk, the other alternative, is to be too simple. So people will say, okay, we traveled up to Udine, we arrived in Udine, and then he's telling us very trivial things and we are wasting our time. Well, I prefer the second risk instead of the first one, especially because Professor Frankfurt, Professor Gavrilyuk, Professor Berdichevsky will feel, and myself, will feel this strain of complicated formulas soon. So these technical difficulties will arise immediately. But I want to try to establish a common language and a common philosophy. And I want to assure you that the ideas we are talking about now are very old. Metrodon was a pupil of a famous Greek philosopher, Epicurus. And this statement, in my opinion, is the first statement of epistemological modern philosophy. In my opinion, Metrodon is stating that using equations you can forecast the behavior of systems, physical systems. Of course, there is a controversy. I advise all of you to read a wonderful book by Professor Lucio Russo, who his Forgotten Revolution, in my opinion, is one of the most beautiful intellectual achievements in the last years. He established, in my opinion, that science was born in Hellenistic era, something like 2,300 years ago. Metrodon is of this epoch. Controversies are that I am also from Naples as Professor Russo, so we are philosophers of Magna Graecia, you know, the big Greece in South Italy. So people say that we claim this because we want to be the first in having known something. Okay, so if somebody doubts that this is the actual content of Metrodon, then go ahead. This is the fragment from which the translated English statement, translated by myself. I couldn't find any translation. I found a translation from this into Italian. I'm not good enough in Greek for doing this translation. But I translated from Italian to English myself. So, now, but I will stop immediately this discussion about history, at least for the moment. In recent times, a lost Archimedes book has been rediscovered. And in this book they found variational principles. He has solved the technological problem of finding the optimal shape of a boat for having the stable configuration with the vertical position. So, variational principles are very old. Most likely, Pierre de Fermat, and French people being here present, forgive me, was reading Greek books and then reformulating the statement in French. But this is another story. Now we start talking about the principle of least action and the format which principle of least action gives us for building any theory. What I like about Professor Frankfurt papers is that he's dealing with dissipative processes, intrinsically dissipative processes, and he uses variational principles. You should not believe that variational principles and least action principles in general are applicable only to non-dissipative situations. This is a statement which we will discuss in more detail. So, actually, we want to discuss about this epistemological principle. How we are developing, in a sense, the theory of how building theories. This is very Hellenistic, believe me. This is the idea of Greek people. We need to think before starting thinking. This is beautiful. So, the principle of least action tells us how to construct a mathematical model to be used for describing the world and for predicting the evolution of the phenomena. Now, how to do this? The recipe is here. You start finding kinematical descriptors. So you need to model the states of considered system. Then you introduce motions, so you model the evolution of the systems you are describing. And finally, you ask nature and you ask her what you want to minimize, and you introduce the action functionals. Okay? Please follow always the ideas of methodology. Mathematics on one side, reality on the other side. Never confuse the equations with a physical system. Equations are modeling physics. Reality is something. Mathematics is something else. But I will stop here, otherwise we start a Platonic discussion and somebody will say that I'm old and talking about too much philosophy. So, a configuration is the mathematical model describing the state of considered system. So, keep always in mind, configuration, state, they are two different objects. The motion is the mathematical model describing the evolution of considered system, and you need a c-valued function defined on the time interval. So you have a function which at every instant tells you which is the configuration, And the action is a real valued function defined on the set of admissible motions, and this action models the preferences of nature. So I like to do this modeling scheme for making the distinction. A good model uses mathematics for finding the motion which minimizes action. If this mathematics gives you a reasonable forecasting of the observed evolution, then your model is valid. Of course, usually you must keep in mind the following thing. Not everything is described by a model. Theory of everything is non-existent. So a model is always focusing on a set of phenomena. You declare at the very beginning what you want to describe, and then you are wise, and you don't apply this model to other things. I will tell you, just for reassuring Professor Meyer about our, at least, intentions towards applications. I have discussed a few days ago about a variational principle with an engineer who was designing a roof. Okay? You need always to apply the right mathematical model for designing something. If you have a multi-layered beam made of layers of wood and glue, it is not wise to use Saint-Venant model in which every section is a rigid body, because your equations will not tell you what happens in the reality. So the wise man uses always the good mathematical tool for forecasting the right phenomena. Okay? Now, knowing that French people were present, La cinématique d'abord. This is D'Alembert. Be worried when you read a book in which they start talking about forces on the first line. You must be worried. People talking about forces without specifying kinematics before are dangerous. Okay? I'm old. I completed my process for career, so I can talk freely. Okay, and I must thank Professor Meyer for this freedom, because he was the president of 2 of these committees. You know who is the guilty of this. So, the most fundamental step is to decide which is the admissible kinematics. So you need to specify your space of configuration and your motions. Then you can ask yourself, which are the desires of nature? I used the word utility because I want to be suggestive. I was teaching for 3 years mathematics for economical sciences. In economics, they talk about utility, and they apply variational principles for optimizing utility. So, utility of nature is a real valued function defined on the set of motions. Not all admissible motions are accessible. Maybe we need to stop a little moment. We will discuss later about motion of a fluid in a porous matrix, and you will have a discontinuity surface in the solid matrix At this discontinuity, you will have continuous displacements, but discontinuous deformations. I have read a lot of books about continuum mechanics of porous media, and I couldn't understand very much what was written because they mix in a unique bottle, they shake kinematics, forces, configurational forces, whatever they invent, and they use this in a completely chaotic way. While if you read the book of D'Alembert, half of 18th century, you read open. Start with specifying admissible motion. In the context of flow in porous media, continuous displacement, discontinuous deformation, however, with Hadamard condition at the discontinuity surface. Okay? The same will be true for all lecturers and all lectures you will hear here. Everybody, all lecturers will tell you which is the kinematics, and then they will minimize action in the set of admissible motions. Of course, there are some conceivable motions which are not accessible. So you need further limit your consideration to accessible motions. Then mathematics starts, because the real motion will be chosen by the system minimizing the action on the subset MA. I have read when I was young the book of Arnold, the late Arnold. He is dead a few months ago. The book Arnold. 1 month. Arnold wrote a book which is wonderful, head-breaking, but when you are young you need to break your head with this kind of stuff. Arnold states that he will not break tradition and he will not be able to explain clearly Maupertuis principle of the least action. So I dare to explain you, but only in a few sentences, this. When you minimize action, you must specify the set of motions among which you look for minima. Okay? So the choice of Lagrange is you choose the set of isochronous motions. Two motions are isochronous when they both start at a given instant t0 from a given configuration and arrive at the same instant in the same configuration. So you know when and where you start, and you know when and where you stop. So your set of motions is specified in this way. Maupertuis is dangerous because he wanted to do a theology of physics which is too idealistic for my taste. However, he had a good idea, so we shouldn't kill everything conceived by Maupertuis only because of his theological fixations. Maupertuis is fixing the starting configuration, the ending configuration. However, the instant of starts and stop is not specified, but he's limiting himself to conservative systems and he keeps energy fixed. So, the set of accessible motions is constituted by all motions which have a constant energy content. I believe that the reason for which a lot of people wrote and believes that least action principle is valid only for conservative systems is related to the choice of Maupertuis. So we skip this choice and we go ahead with Lagrange. By the way, for French people, even if Lagrange is in Pantheon, he was Italian from Turin. And allow me a joke. Lagrange was a genius of optimization and optimal choice. Young student, he managed to persuade Euler to accept his priority in Euler-Lagrange equations. He went to Berlin and he managed to be the preferred mathematician of the king there. Then he moved to France and he married Cassini's daughter, 40 years younger. And Cassini was very powerful, and this lady was very rich. So, you know, he was very good. And the witness of his marriage was the king. When they killed the king, he became the preferred mathematician of the revolution. And when Napoleon became powerful, he became senator of Napoleon. And after being dead, he managed to be Pantheonism. He was sent to the Pantheon. So, you know, variational principles are very good. Believe me, if you handle them, you may become very powerful. You know, this is the epoch of money, advertisement, you know, we joke a little. Okay, so open a book. I have printed 150 books in calculus of variations for being ready. I couldn't study all of them. For being ready for these lectures. And believe me, in every book of calculus of variations, you find historical comments, and somebody starts talking about history, and you have always Greek mathematicians quoted. So here I follow this. And Olympiodorus, this could be agreed by all, that nature does nothing in vain, nor labors in vain. This is our principle. France is one of the most beautiful countries. I like it very much because it is not Germany, but it is a country. It's not like Italy. Italy, we don't have state, we don't have rules, we don't have anything. In France, rules are more or less respected. La nature, dans la production de ses effets, agit toujours par les lois les plus simples. The problem is, what is utility? We have to understand what is utility. And now I could start with hard mathematics. Because finding minima is a difficult job. We follow Lagrange, la mécanique analytique, and we limit ourselves to Lagrangian functionals. We should understand how these ideas arrived in Russia. I think that there is a dynamical phenomenon. When you have a revolution somewhere, variational principles start being studied in that country. This could be a rule to be proven with some mathematical tools. We need, everybody knows that when you have a real valued function, you need, for finding maxima or minima, you need to estimate derivatives. And now, action is a function defined in the set of motions, not real numbers. This is the true difficulty of what we are trying to do. So, we need to understand what is an infinitesimal variation of motion. We need to find a differential of a functional, and we need to estimate the order of infinitesimals of this. So you need Frechet and Gateau derivatives in manifolds with maps in Banach spaces. So I tell you that I'm good in mathematics. Okay? This is the right frame for mathematical frame for studying this subject. But Lagrange did not know anything about Banach space, and he ignored everything about Frechet derivatives, even if he could calculate them. So our strategy must be rather to follow, at least here, at least now, to follow Lagrange strategy, at least for what concerns my lectures. Of course, I cannot be sure of. I've seen Sergei's lectures, so I'm sure he's following my philosophy. So, we need to discover what is a Taylor series for action, and we need to find the first variation of action, and then we want that this first variation is equal to 0. And we get the evolution equations of our system. Now, in this presentation, I will not tell you in details what we will discuss in the others. One big problem with people who plays with balance equations and forces is that they never find, they are not good in finding boundary conditions. And I've seen books, papers with wrong boundary conditions. In my last paper with Pierce et Pecher, I have reviewed 195 papers in which people tried to find the boundary conditions which were found in 3 pages of calculations. And we are more general. Principle of list action is a powerful tool because it gives you not only bulk evolution equations in the volume if you have fields, but also the good corresponding boundary conditions. Now I have started reading the ancient papers, for instance, of Kossera brothers or of Euler. Everybody who produced true original stuff, they always used variational principles. You know, in the theory of beam, they talk about contact actions, momentum or shear forces or normal forces, because Navier decided one morning to write a polycopy pour l'école polytechnique. And somebody told him, be simple, be practical. He forgot all deduction and he wrote final equations, and then with physical sense, he explained the good boundary conditions found with a variational principle. When I was young, I started to have physical intuition for finding boundary conditions. I never found good boundary conditions. Never. Only when I met people from the French school who started calculating first variations of something, then I found good boundary conditions. So maybe our Russian friends will talk about Kognov, or so let me play a little. This is beautiful. Only in France you find a statue, La nature se dévoilant à la science. This I like very much of French people. There is a faculty of science, and the stairs of marble stairs of this faculty has at the top this statue, a copy of this statue. Okay, I add to this that of course, pour dévoiler la science, il faut une Lagrangien. for unveiling science, for unveiling nature, you need a Lagrangian function. So let us go now in some technical details. Also this you can find in a standard book. I'm not telling you that I'm doing original things in this moment. This, I wanted to write you a general form of all equations which will be shown to you. Psi sigma is the set of fields we introduced for describing our configuration. So the motion is given when you know psi of c, because you know if you include time in your variables, then you get a function and everything is standard. So you have capital T, the hypervolume of the n-dimensional space whose variables are xm, and we decide to find minima for this function. Be aware of the fact that this is a very particular function. You have a field, a set of field psi sigma. You estimate their value in x mu. You estimate their gradient in x mu. Then you calculate the Lagrangian of this, you get a function of x mu, and then you integrate this. So, for instance, if you want to do the mechanics of second gradient materials a la Germain, because Paul Germain did this new theory in the 70s, this approach is not good. You need to add second derivatives of psi sigma over the mu. Okay? So already if you have another ingredient, another gradient, this Lagrangian must be changed. Okay? But let us reason about it in this shape for the moment. Then you consider, this is the trick, you consider psi sigma plus epsilon eta sigma. Eta sigma plays the role of a vector, the small vector of variation of your motion. Okay? And look, when I've read that delta, the first variation of action, which we will estimate now, was estimated by Lagrange when he was 17 years old, I was very upset. Because I understood that I was not Lagrange. Okay? The clever idea is the following. Think that he has done this when he was really young, and in an epoch where the Taylor series was the subject of very advanced classes in calculus. It was not taught to first-year students. So the idea is to consider the variation of L before integration and to estimate the Taylor series in this way, and then integration by parts, and after this integration by parts, consider eta sigma equals 0, arbitrary. Okay? So you say, in every direction where I change my motion, I get always the first variation of the action vanishing. Everybody who studied calculus knows that this is the condition by which you get that the first derivative of a real valued function, or the gradient of a real valued function, must vanish when you attain maxima or minima. And after, of course, you need Lagrange theorem. You need to know that all fields are suitably regular. Of course, I could tell you now that the Hilbert space where you are estimating this inner product, because integral of the eta s times the bracket, this is an inner space in a functional space, Hilbert functional space. But let us follow a little bit the flow of ideas of Lagrange. If eta s is arbitrary, and this is what then has been called virtual displacement or virtual variation of the motion, then you get this bulk evolution equation for your system. When you perform integration by parts on the boundary of T, of course T has two kinds of boundaries. Time type boundaries where delta psi is vanishing because we are using isochronous variations. On the space type boundaries, you get the flux of dl over what is in that divergence operator, the flux of this animal dot normal being assigned, or the corresponding displacement being vanishing. So either you impose a kinematic condition, then you know your boundary conditions, or if you leave kinematics free, then you get the dual boundary condition in terms of sounding, which unfortunately has been called force, dual, double force, configurational force, or sounding, which depends on the particular physical situation you are dealing with. But following Lagrange, we could call it dual. It is the dual quantity of the displacement which is left free. And in every particular instance, you will get information about this dual quantity. Okay. We have written, I think that the inspiring book of the previous calculations are from Landau. I think the source is Landau, but maybe you find it elsewhere. By the way, quantum mechanics has been formulated with variational principles. Everything new has been formulated using variational principles, I'm sure. Okay, like every serious mathematician, now we consider a particular case, n equal 4. We get space-time. And in this case, the divergence is the space divergence and the time divergence. And the gradient of psi sigma is space gradient and time derivative. And I'm sure that everything you will see in these lectures, maybe in a painful way, but can be put in this form. For instance, I have some minutes, so I was worried that I could talk too much, but I discovered that I was estimating in the right way the time, so I can tell you this. For instance, let's be a little bit proud of Italian scientists. There was a mathematician in Rome called Cattaneo, Carlo Cattaneo. He discovered that heat equations were bad. Why they were bad? If you switch on in a given point a heat source, you get a signal at plus infinity. So you have a signal, the speed of which is plus infinity. Okay? Do you believe this is related to the fact that there is no Lagrangian version of heat equations? Now, he replaced in heat flux a slightly different constitutive equation with respect to the standard one. Heat flux proportional to gradient of temperature. He added, a clever way, a delay, and he got Cattaneo heat equations with a finite speed wave. You can bet, and you are right, that these equations are Lagrangian. If you play tricks with nature, so you force it not to be Lagrangian, then you find signals traveling with infinite speed. Now, somebody wanted to formulate a different format for theories, or at least mechanical theories. In particular, Paul Germain wanted to avoid this controversy about is least action general or not? Are you including dissipation, yes or no? So he wanted to avoid it, and he formulated the principle of virtual powers. Now, it is clear that if you introduce an action, you split it in internal action, external action, inertial action, you write that first variation of action equals 0, derivatives even for function. Okay, Frechet derivatives are linear. Okay, so we can write delta internal action plus delta external action plus delta inertial action equals 0. And so, with suitable identification, you get the principle of virtual powers. So it is trivial to remark that if you accept the principle of virtual power, you are more general. However, are you really more general? There is a terrible controversy about this. And so, I don't dare to talk with details this mathematics. And I even refuse to write equations about this. I tell you something. If you have a system which is not Lagrangian, so there is no Lagrangian for describing this motion, exactly as in the case of Cattaneo equation, you have forgotten something. So you must add some kinematical descriptors of some phenomena you are not including in your first frame. Okay? So, if you enlarge a little bit the kinematics, you can write a least action principle more general, and your particular subset of kinematical descriptors will evolve as a part of the big one. Okay? Of course, this is handshaking. You need serious mathematics for doing this. This has been started by Helmholtz and has been continued by Russian school. So this is a very serious field. But I tell you that also with the old Lagrangians and a limited set of kinematic variables, you can even describe many dissipative systems. Okay? So I believe that the epistemological principle I'm trying to defend here is rather well grounded. But we need to survive. You know, this is typical of Italians. Even if Hamilton and Rayleigh are British, we need to survive. So instead of attacking the difficult problem, embedding a Lagrangian system in a non-Lagrangian system in a more comprehensive Lagrangian system, we can use the so-called dissipation functional a la Rayleigh, Hamilton-Rayleigh. You introduce an action. You integrate by parts and you find the right boundary conditions. Then you discover that energy is not conserved because there are some phenomena, but you are not blind. You know what is dissipating energy. The dual quantities you have found with integration by parts, or the source terms in the bulk equations. So you don't postulate dissipation in a blind way. You introduce a dissipation function, which is a definite positive function on the velocities which of the motion you are considering, and you have the dual quantities which are spending power on these velocities. This is standard. I mean, this has been accepted by everybody. By the way, you should remark that even if French people are more variational and in general Anglo-Saxon people are less variational, this is not true in general because Cauchy was against variational principles, Navier was against variational principles, Hamilton and Rayleigh gave us the tool for attacking dissipative phenomena using, I will tell you, there are clever people and less clever people. Even if it is dangerous to say this about Cauchy, I mean, Greek people said, also Homer sometimes sleeps. Okay? For meaning that also Cauchy sometimes can say something wrong. Okay? So, we should never accept that something said by Lagrange or Cauchy is true by hypothesis. However, I will tell you that I have not found any statement by Lagrange who is wrong, but I mean, maybe it is my fault. Okay, so I think I can stop here, but please, the brand of my group is now this one. In nomine est natura rerum. This is for defending mathematical formalism. Imagine that I tried to talk to you about the first variation of action using words without writing integral of the Lagrange. I mean, this is absolutely crazy. So I need to introduce names, formulas. Nomina sunt consequentia rerum, however, because we are not blindly building mathematical models. We get information about physics, and from this information, we formulate our models. Okay? So I conclude asking to the persons who already knew all this to be patient. In my opinion, this kind of discussion was required. To those who believed that variational principles are valid only for conservative systems, I say, please consider seriously our point of view. It is old. Archimedes started. And it is valid. It worked. Okay? Okay, thanks very much.